Before moving on to the new topic, constraint satisfaction in AI, let us quickly recap what we have studied. We have gone through searching algorithms in the previous classes. It is broadly divided into two as uninformed and informed searches. In the uninformed searches, we have seen various forms of DFS, then BFS. The other one was cost first search. In the informed search, we made use of information which is called as heuristics for proceeding with the algorithm, and in that we have seen best first search by the use of A-star searching, problem reduction using Andor graph, generate and test algorithm, and finally hill climbing algorithm. Now we are left with two more algorithms in heuristic searches or informed searches. They are constraint satisfaction and mean scent analysis. For the time being, we will be considering constraint satisfaction. So it's called by the name CSP, meaning constraint satisfaction problem. Constraint means some conditions to be followed while making operations. So I'll be using the term CSP in future. CSPs are mathematical questions or problems defined as a set of objects whose state must satisfy a number of constraints or limitations. So for solving this problem, we may have to use operations. Not only that, we have to obey some more conditions for making that operations. Many problems in AI can be considered as problems of constraint satisfaction. Here, when we go for the goal state, it should satisfy the number of conditions or constraints associated with it. CSPs can be solved by using any of the search strategies we have seen. Only the limitation is that with these strategies or searching algorithms, we have to go with the constraints or conditions associated with that operations. The general form of CSP can be considered as follows: until a complete solutions, that is a successful searching, is found, or until all the paths have led us or taken us to a dead end, which means unsuccessful search. We have to follow these steps repeatedly. We have to select an unexpanded node of the search graph, which we were doing so far. The same step has to be done. We have to select a node which is not expanded, meaning what? We have to select a node where we have not applied the valid operations. So we'll be expanding a node to create new nodes or new states. And on selection of this node, we have to apply the constraints or rules that are associated for applying the operations. Now, if the set of constraints contradicts, if the rules are not followed for that operations, then we consider the path as a dead end, because we cannot proceed further in that path. Then we may have to go back and apply new operations with new conditions or constraints. If the set of constraints describes complete solutions, we treat it as a success. So when the conditions are followed or obeyed fully, we can say that we have reached to a goal state. In neither of these cases, if 3 is not followed or 4 is not followed, we have to apply the rules to generate new state. So we are not ending up with a dead end, or we are not ending up with the goal state. We have to repeat these steps with applying these conditions or constraints over the current state. So these steps are repeated again and again until one of these, either step 3 or step 4, is reached. Now the CSP requires with some limitations or conditions which are known as constraints, and is defined using a triplet V, D and C, where V stands for variables, D are the domains of that variables, and C stands for the constraints. So it is defined as a triplet where we will be having a set of variables v1, v2, etc. vn. Each variable vi has a domain di of possible values, because v can take some values, v2 can take some other values, v3 can take some other values. Likewise, each of the variables will be having their own domains, valid values for acceptance as the value of that variables. So that is the relation between v and d, or vi and di for all values of I. Then we must have a finite set of constraints or conditions to be applied on the operations. They are represented as C1, C2, etc. Cn. Each of these constraints relates to these variables, and by specifying valid combination of these values, we will be applying these conditions for proceeding with the next state or valid state. Finally, when we reach a goal state, we should make sure that all the conditions or constraints are satisfied. Otherwise, the goal state will not be considered as a successful finding. There are some examples for or models of CSPs. Some of them are n-queens puzzle and map coloring problem, the famous Sudoku, then Boolean satisfiability. I have made or posted, I'll be posting some videos on this. You can make a reference. I will explain one among these. Let it be the first one itself, n-queens puzzle. I am considering the value 4 for this n, so this will be a 4-queen puzzle. If it is a 4-queen puzzle, we have to consider a board having 4 rows and 4 columns. It can be considered as a chessboard. Normally chessboards will be having 8 columns and 8 rows. Then we will be having 8-queen puzzle. To make it simple, I am considering half of it, that is a 4-column 4-row matrix, 4-row by column matrix, 4 by 4 matrix, which will be having 4 queens to be placed. That is the problem. So if we are using as such the board as such and the coins as such, we will be having 16 C4 combinations available. It will be a very large number. The combinations will be large in number To make it small, we are applying the following constraints. The constraints says that no two queens should have the same row or the same column or the same diagonal. That means I hope that you are knowing the movements of queen in a chessboard. When the queen is in straight line with other coins in the board, it can be either in the same row or in the same column or in the same diagonal. They are under threat. So similarly, when we place many queens on a board, they should not be under threat in any manner, either with the row or with the column or with diagonal placings. So this is one of such placing. Let me consider this queen for explaining this board position. This queen doesn't have or doesn't share the column or the row or any of the diagonals. So is the case with the other three queens. So we have to place the number of queens in such a manner so that none of them are under threat from others. Solving such problems comes under this CSP, because we are having some constraints for finding the goal position.